Welcome to the last lecture of this section. In this lecture, we are going to learn about Josephson effect and applications of superconductivity. Josephson effect. Consider a thin insulator sandwiched between two superconductors as shown in the figure. It is observed that a current flows through this superconductor-insulator-superconductor junction under suitable condition. This is termed as Josephson effect. This can be explained on the basis of quantum mechanical tunneling of Cooper pairs. Wave function of Cooper pair on each side of the junction could penetrate the thin insulating layer, exponentially decreasing amplitude. As the junction is very thin, they overlap and couple together and pass through the junction. There are two types of Josephson effect, AC Josephson effect and DC Josephson effect. If a DC current flows across the junction, even in the absence of any potential difference, it is termed as DC Josephson effect. Let's have a look at its proof. Let psi1 and psi2 be the probability amplitude of wave function of superconductors on both sides of the insulators. Then, time-dependent Schrodinger equation can be written as I h cross dou psi1 by dou t equal to h cross t psi2 and I h cross dou psi2 by dou t equal to h cross t psi1, where t represents the transmission rate from one side to other. It has a dimension of frequency. If psi1 is equal to half n1 e raised to I theta 1 and psi2 equal to half n2 e raised to I theta 2, we can find dou psi1 by dou t, dou psi2 by dou t and substitute for psi1 and psi2. After this, multiplying first equation by n1 raised to half e raised to I theta 1 and second equation by n2 raised to half e raised to minus I theta 2, we get these two equations. We know that e raised to I delta is equal to cos delta plus I sin delta. Using this expansion and equating real and imaginary parts, we get these four equations. Apply the condition that for an identical superconductor, N1 is equal to N2. Thus, we get dou theta 1 minus dou theta 2 by dou t is equal to 0. That is, rate of change of phase difference is 0 or phase difference is a constant. And dou n2 by dou t is equal to minus dou n1 by dou t. Thus, we can write current through the junction as I equal to I0 sin delta, where delta is a constant phase difference. Thus, a maximum current of magnitude I0 and minus I0 flows across the junction. This is DC Josephson effect. AC Josephson effect. If a DC voltage is applied across the junction, RF current oscillations are produced across it. This is termed as AC Josephson effect. In order to produce AC Josephson effect, we have to apply an external potential. So, the potential experienced by the charge on both sides of the insulator are QV and minus QV, where Q is equal to minus 2E in the case of a superconductor. Then, time-dependent Schrodinger equation in this case can be written as IH cross dou psi1 by dou t equal to H cross t psi2 minus EV psi1 and IH cross dou psi2 by dou t equal to H cross t psi1 plus EV psi2. Proceeding in the similar manner and equating the real and imaginary part, we get d by dt of theta 2 minus theta 1 equal to minus 2 EV by H cross. On integrating equation 3, we get delta t equal to delta 0 minus 2 EV t by H cross. Thus, equation for current through the junction I equal to I0 sin delta 0 minus 2 EVT by H cross. Thus, an AC current which oscillates with a frequency of omega equal to 2 EV by H cross is produced across the junction. This is AC Josephson effect. Following are some of the applications of superconductors. Have a look. We have come to the end of the session, superconductivity. Hope all of you understood the topic well. Thank you and all the best for your exams.